water potential? How do we know that the pressure probe is measuring pressure potential that's believable? Well, Ken Shackle did some comparisons as a series of other experiments that we'll get into talking about stomata. But he used this plant Tradescantia spiderwort, and he used a pressure probe to measure the pressure potentials in epidermal cells, individual epidermal cells. And he used 2 in situ cycrometers to measure total water potential at different points of the leaf. So his setup looked like this. He was doing gas exchange measurements and stomatal conductance. Let's not get into that now. But here's a leaf from this spiderwort where he's got a in situ cycrometer here, another one here, and then a pressure probe that is poking these epidermal cells with right here. This gives total water potential, this gives total water potential, this one gives pressure potential. And he wanted to compare these. Let's think about what he's comparing. The in situ cycrometer, that little, this thing. What water potential is that measuring? In an ideal world when everything's working, what water potential is that measuring? I'm asking you. Let's say this is the piece of leaf enclosed in that little chamber. There's a lot in there. What water potential is that thing measuring? It's measuring some average water potential of everything in this space, right? And probably weighted by the volume of all the different components. Mostly, as you say, it's these cells right here. They have by far the biggest influence. But let's think. When that leaf is not being measured, the water potentials in these different cells are different, especially when the leaf is transpiring, because you know the water is coming from the xylem. It's moving out from the xylem into the spaces around these cells, the cell walls, and into the cells. Eventually, it's evaporating into the air spaces and diffusing out the stomata to the atmosphere. So there's a gradient in water potential from the xylem to the epidermis of this plant. And when you stick this in your chamber, you're measuring some sort of average that's higher than the water potential here, but lower than the water potential here. Right? So here's some of his data. Okay, here's the total water potential at the tip of the leaf and the base of the leaf, and here's the average. So here's his leaf water potential. His osmotic potential he measured by sucking out some of the sap from the individual cells and determining osmotic potentials by freezing point depression using a nanoliter osmometer. So don't worry about it, but he was able to quantify the osmotic potential. Here's the total water potential, here's the osmotic potential, here's the pressure potential that he measured with the pressure probe. And then he was doing experiments here, let's not worry about the changes. So the question is this solute potential plus this pressure potential equal to this total potential? That's the question you have. And believe it or not, it wasn't. But the difference, so here's the pressure plus the osmotic, using 2 different techniques, minus the leaf water potential, now using 3 different techniques to determine these water potentials. That difference, that discrepancy between these 2 and this, depended on the transpiration rate from the leaf. So he plotted that difference as a function of the transpiration rate and extrapolate back to 0 transpiration when all the water potential should be the same in all those cells if there's no transpiration going on. And got an error, let's call it, of minus 0.05 megapascal. Not bad. So he said, it's not bad. These devices are working pretty much like we think they are, and they make consistent measurements relative to each other. go. Okay. All right. Have a good weekend. See you on Tuesday.